In this video, we are going to look at how the greenhouse effect actually works. I said in the previous video that it's subtle but important, the differences between how it actually works and how it is often portrayed. But first I wanted to talk a little bit about the syllogism that I set up in the previous video, and this is the syllogism that I'm going to be kind of following, and I wanted to show that there is a missing premise from it that I assumed in the previous video. I think most people will uncontroversially think that this is true, but I did want to point it out explicitly. And so it looks like this P9 here. If a thing does something that causes radiative forcing, which is what's talked about in P3, resulting in increased or decreased, if that's the case, global average temperatures, which is what's talked about in P4, then that thing is at least one of the causes of climate change. Again, I think this is uncontroversial. It's just saying that if you cause radiative forcing, then you are also the cause of climate change. Again, this was unstated, but I do think it's uncontroversial. So in the previous video, we looked at the fact that we have these carbon emissions, and we concluded that human activity releases excess CO2 into the atmosphere. We can see that because we can just measure the amount of CO2 in the atmosphere, and it is increasing, which means that human activity is releasing excess CO2 into the atmosphere. Then we also looked at this, where we looked at the difference in the amount of energy coming in versus the amount of energy going out, and we concluded that there is no other mechanism other than heating up the earth for mitigating the extra added energy. Then we also looked at the fact that CO2 can take hundreds or even thousands of years to actually leave the atmosphere, and so we concluded that there is no mechanism to quickly remove all excess CO2 from the atmosphere. This P8, as I said, is going to have to wait until video 4, where we talk a lot more about CO2 and why it's a greenhouse gas, but we will get there. In this video, we're essentially not going to be affirming any of these premises, but we will be lending support to these ones that I have highlighted in green here. So that's what this video will do, but it will also be talking about how the greenhouse effect actually works, while also giving some important definitions here up front. And so that's going to be important going forward for just knowing why certain things like greenhouse gases or the different cycles that we're going to be talking about in the next video are actually contributing to climate change. So we looked at this in the previous video. Again, this is just showing that there's at least a correlation between the carbon dioxide and the temperatures. In video 4, we'll talk about why carbon dioxide is the thing causing this, but for now, all we know is that there is a correlation between carbon dioxide levels and the temperature. I also wanted to point out this study here, which does essentially the same thing as most other studies. It uses kind of a state-of-the-art statistical method, and so that's why they have a bunch of these different things here. So they have a bunch of acronyms. And so what I wanted to show, because this is a popular talking point for deniers, is that we are not just coming out of an ice age. I mean, we are kind of on a geological time scale, but the rising temperatures is not because of the ice age coming to an end. So what we can see here is that there is about 8,000 years of the temperature being relatively steady. If you zoomed in on that, you would see that there is variation, but compared to the variation between an ice age, which is what's going on over here on the left, and what was going on for the previous 8,000 years is quite a bit different. So the variations in the last 8,000 years are quite small compared to what you see when you are coming in and out of an ice age. But then what we see is in the past 150 years or so, there is now this sharp increase. So this looks like it's disconnected from this climb out of the previous ice age. And so that shows that the warming trend is not just because we are coming out of an ice age. But anyway, I wanted to throw that in real quick because I think that's an important thing to pay attention to. So when we're talking about climate change, we do have to make a few assumptions. These assumptions tend to be quite justified, but they are assumptions that we should state up front here. So the first one is that the only source of energy heating the planet is absorption of light from the planet's host star, which for Earth would just be the sun. The heat coming from the center of the Earth or from other stars is negligible. The next one is that the planetary albedo, or the proportion of sunlight reflected by the whole planet, is spatially uniform. So essentially we are modeling the Earth as just being one single color that has all the same albedo. We know for a fact that it is not uniform. there is oceans, there's land, there's clouds, there's all kinds of stuff going on. But approximating it as uniform obtains acceptable results. And the other assumption is that the planet is spherical and has a distinct solid or liquid surface which radiates like a perfect black body. So in reality, it's more of a gray body, but again, the black body assumption obtains acceptable results. So it's a gray body because there is the albedo, so there is some reflection going on, but all of the energy that gets absorbed is then re-radiated as a black body. And we can see here that this is a decent assumption because we see on this line here, that would be what the temperature would be if we had zero albedo. So we see the temperature on the y-axis. This normalized orbital radius is just how far away from the sun it is. But we can see here that most of these lie quite close to this line. They're slightly lower because they do in fact have albedo, and we can see that Venus actually has quite high albedo. We'll talk more about that in other videos, but we can see that if they were perfectly acting as black bodies, if they had no albedo, they would lie right on this line, but we can see because of the albedo they lie somewhat below it, but not by very much. So again, this black body assumption tends to get acceptable results. So when we are thinking about climate change and how it works, what we're really thinking about is what's called the energy balance. So the conditions that must be met for the average temperature of the planet to remain constant is that the amount of energy coming in has to be equal to the amount of energy going out. When we have what's called radiative forcing, and this is caused by greenhouse gases amongst other things, then what we would see is that the amount of energy coming in is greater than the amount going out. And we know from the previous video that this is in fact the case. We know that there's more energy coming in than what's actually leaving the planet. And how does this lead to increased average global temperatures? That's because temperature is related to the amount of energy by this equation right here. So we can see as the energy goes up, the temperature is also going to go up. So we need to talk about a few definitions here. One that is important that comes up all the time in the literature is what's called the lapse rate. So this is the rate at which a parameter changes as altitude increases. This is usually used in the context of temperature, which has a lapse rate of about minus 6.5 degrees centigrade per kilometer, meaning that for every kilometer you go up in the atmosphere, every time you go up a kilometer in altitude, the average temperature goes down by about 6.5 degrees Celsius. Pressure is a little bit more difficult because it declines exponentially rather than linearly. Then the next definition is what's called the solar constant. So this is the power in watts that will hit a square meter of space at some distance from the sun. This is usually denoted as S for solar, sometimes L for luminosity. The book that I was using for this used L, so that tends to be what I use for this, even though S tends to be the more standard version of it. And we can see that for Earth, at an average distance of 1.50 times 10 to the 11 meters from the sun, the solar constant is, on average, about 1,361 watts per square meter. And so what I mean by all this, we want to look at this pictorially. It looks like this. So we have the sun at the center of our solar system, and that has a radius of 0.00464 astronomical units, or 6.96 times 10 to the 8 meters, where astronomical units is just defined by how far the Earth is on average from the sun. And so this is the radius of the sun right here, but then we have the Earth that's orbiting it, and that's orbiting at a radius of 1 astronomical unit. That's just how we define astronomical units, and that's 1.50 times 10 to the 11 meters. And so when we're saying that the solar constant is 1361 watts per square meter, it's 1361 watts per square meter at the distance of the Earth. So to get what the solar constant is at some distance, we have to use this equation right here, where this R is for the radius of the sun. This sigma right here is just a constant, and it's this right here, the 5.67 times 10 to the negative 8 watts over meters squared times Kelvin to the 4th. Then we have the temperature of the sun, which is raised to the 4th power, and that temperature of the sun is about 5,778 Kelvin. That is at the surface of the sun anyway. Then this capital R down here is just distance of the orbit from the sun. So this is going to be a function of this big R right here. And so like I said, at the Earth, this gives us 1361 watts per square meter. But if we looked at this for something like Venus, then it's 2,601 watts per square square meter. That's at 0.72 astronomical units. And then for something like Mercury, that is at 0.4 astronomical units, and that's 9,116 on average. So if we plotted this function right here, it would look like this. So I'm using Desmos, I just put this in. I'm using astronomical units because that's a bit easier to visualize on here. And so the plot looks like this. Then we can place the first 4 planets on here. So Mercury at 0.4 astronomical units is right there. So this plot right here is not at a lot of significant figures. So we can see that these are slightly off from what it actually is. And even these actual ones are just averages, because especially something like Mercury has a pretty eccentric orbit, and so it's not always receiving the same amount at every point in a Mercury year. Even that right there is just an average. Then for Venus, that shows up right here. So again, this is slightly off from what it actually is, but it's about 2601 watts per square meter. Then for Earth, which is at 1 astronomical unit, that's the units on our x-axis here. So that shows up at 1361 watts per square meter at 1 astronomical unit. Then Mars, which is at about 1.5 astronomical units, has a solar constant that's in the ballpark of 600 watts per square meter. This other important definition here is what's called the OLR, or outgoing long wave radiation. So the infrared radiation leaving Earth is called OLR. This is how the vast majority of energy leaves Earth. That's because out in space, where there's only vacuum, there is no conduction or convection of energy. So only by re-radiating it do we actually lose that energy. We also don't lose very much material into space. Very light elements like hydrogen and helium can get lost out into space, but most of the gases in our atmosphere remain in the atmosphere. And so the energy that we lose is pretty much all from this OLR. And they call this long wave because the infrared is long wave relative to the incoming light, which is mostly in the visible range. The OLR at the surface, by the way, is going to be greater than OLR at the effective emission height due to absorption of energy by the atmosphere. So you're going to be losing more energy in the form of this radiation right at the surface than you would up higher in the atmosphere, and that's because the energy gets captured by the atmosphere. So this is what it looks like, where this on the left is the short wave, so this is the incoming radiation. We can see that a lot of this is in the visible spectrum. That's why we evolved to see things in the visible spectrum. But then the long wave is going to be in the infrared over here. So we can see the wavelength down on the bottom. We are going to be over here centered around 15 microns. And so this is the long wave radiation that's outgoing right there. That is the thermal radiation coming from the surface in particular. And we assume that that is essentially just blackbody radiation. That was one of our assumptions from earlier. So one more definition that we need before we move forward is what's called the solar irradiance. So this is the power in watts that actually hits a square meter of the Earth. So this is calculated by taking a cross section of the Earth. So if you're just looking at the Earth from one direction, it'll look just like a circle. And so that will have units of square meters. And so we multiply this by the solar constant. We just use the pi r squared, where r is the radius of the Earth, and multiply that by the solar constant of the Earth, which is that L sub Earth. And so what we see is it looks like this. The reason we're taking the cross section is because the light coming from the sun is pretty much parallel by the time it gets here, because the sun is so far away. And so it's only hitting one face of the Earth. And the face of the Earth is a circle that can be given by pi r squared for its area. So this is the area of CS, the cross section. This right here is the area of the surface of the entire sphere, which is just the 4 pi r squared. And because the Earth is, despite what you may have heard on the internet, spheroidal, that means these solar rays are going to be hitting it at different angles. Remember, because the sun is so far away and because it's small compared to that distance, the solar rays are coming in essentially parallel to each other. And so we can model it like this, where we can see between each of these lines here, there is a similar amount of area. And so we can think of that as the flux of the solar rays. So if we put something in there that looks like this, that has a certain area, so it has a certain surface area area here, we can see that at 90 degrees, this is going to be intersecting 6 of these bars here. But if we look at it for something at 45 degrees, now it's tilted, so only 5 of these bars are actually intersecting it. So that means that at 45 degrees, we are getting less of this solar flux than what we get at 90 degrees. We get even less at 15 degrees, and we get pretty much nothing at 0 degrees. So when we have a solar ray that's coming in right at the top of the Earth, it'll just pass through the atmosphere and come out the other side. Of course, we know because of greenhouse gases, some of that energy will get captured. But if we're just thinking about the surface, it would just pass right over the surface and keep going. And this is important because since we have this 23-degree tilt on the Earth, this is also why we have seasons, and because of the lower flux of energy at the poles, this is why the poles are coldest. We have the highest flux when we're at the equator. That's why the equator is warmest. Of course, the Earth is orbiting the sun, and that's why this 23-degree tilt will not always be tilted in the same direction relative to the sun, and so that's why we get the seasons, because of this angle at which these solar rays come in. So there's one more definition that we want to talk about, which is called the solar irradiance, or sometimes called the solar insolation. So this is the power in watts that actually hits a square meter of Earth. Remember, the solar constant is how much hits a square meter at some distance from the sun, but because the Earth has things like clouds and atmosphere and other things like that, we're interested in how much is actually hitting the Earth. So remember, the solar rays hit the Earth in a cross section that we can use pi r squared for, where r is the radius of the Earth. Then we want to multiply this by the solar constant at Earth. And so that gives us this right here, this pi r squared times L. But because the solar radiation hits only a cross section, but must heat the entire surface. So remember, the cross section is just the circle that you could see if you were looking at the Earth from a particular direction. But the Earth is spheroidal, so we actually have to heat the entire surface, which is the 4 pi r squared. And so we want to use this right here, where now we see the pi's will cancel out, the r squared will cancel out, so we're just left with the L divided by 4. So this is what these look like. At the top of the atmosphere, that's what TOA means, this is how much solar irradiation is happening. So we can see at the equator here, we're getting a lot. That's because as the Earth rotates around the sun, the solar rays will be hitting anywhere in between here at 90 degrees, depending on what time of the season it is. But then the solar irradiance that's actually hitting the surface looks like this. So remember, there's all kinds of stuff in the atmosphere. There's aerosols, there's clouds, there's all kinds of other stuff that can block some of that radiation from actually reaching the surface. So that's why both of these are in the same color scale, but we see this one for the surface is actually quite a bit less here. But we do notice that most of it is hitting in the equator, and then it gets colder or it gets less energy flux as we go towards the two poles. But like I said, there's all kinds of stuff in the atmosphere that prevents all of this energy from actually getting to the surface. One of those things is what's called the albedo, which is oftentimes denoted with alpha. I've seen it denoted with A before, but alpha seems pretty standard. So this is how much sunlight is reflected back to space rather than re-emitted as blackbody radiation. So we want to make this distinction between what's being reflected and what's being re-radiated as blackbody radiation. For the Earth, alpha is about 0.3, which means about 30% of all the solar energy that comes at the Earth just gets reflected back. So that's not actually heating anything. So only 70% of it is actually heating things. So this is what the albedo looks like. Remember, we said one of our assumptions is that the albedo is uniform over the whole planet, but we know that's not actually true. So we can see here, like places like Greenland have very high albedo, where places like here in the northwest of Upper Canada, where there's probably a lot of forest, there's less albedo. Then we see in places like the Sahara Desert, where there's a lot of sand, there's more albedo. But then in places like sub-Saharan Africa, where there is more jungle, there's less albedo. So if you average all this up, you would get something that's about 0.3. But we can see that it's not actually uniform over the entire planet. But since only 70% of the energy is actually getting to the Earth, we want to use this 1 minus alpha right here. So this will give us 1 minus 0.3, which is 0.7. So we take our L Earth, that's the solar constant at the distance from the sun that the Earth is, divide it by 4, which is what we got up here, then multiply it by the 0.7. So we take our 1361 watts per square meter, that's the solar constant at Earth, we divide it by 4, multiply by this 1 minus 0.3, and we get about 240 watts per square meter. So we saw before that the solar irradiation is not completely uniform over the entire planet, so this is just an average, but on average we see that we do get about 240 watts per square meter. So what we've seen so far, we used this equation here to find out how much energy is actually coming in. We use the solar constant here, which is the L sub sun. We use this equation, we plug that in, and we get 240 watts per square meter. And so the amount of energy coming from the sun that is absorbed by the earth is 240 watts per square meter. But now we want to think about what's called the outgoing long wave radiation. So remember, our radiation balance means that the E in must be equal to the E out. And so we want to find out what the temperature of that E out is. So we use the Stefan-Boltzmann equation that looks like this. Then we just rearrange it so that we can solve for the temperature. And because, remember, if we are in energy balance, then the energy coming in has to be equal to the energy going out. And that means the energy going out would also have to be 240 watts per square meter. So this is what the OLR looks like. Again, we see near the equator, this ends up being quite a bit more going out because it's also where most of it is going in. Then when we get to the poles, we have a lot less OLR. And again, that's because we are getting less energy at the poles because of things like albedo, but also because of the curvature of the Earth. Remember, when it's hitting at that smaller angle, we are actually getting less energy per square meter. But when we are at about 90 degrees, which is in this area here at some time during the season, then it's actually going to be getting the full brunt of the energy from the sun. And so what this means is that if we calculate the temperature that we need to be radiating at, so this is the temperature in Kelvin that the Earth needs to radiate energy back into space, because all of the energy escape from Earth is from radiation, not from convection or conduction. What we find is that the temperature that we need to re-radiate is 255 Kelvin. So the radiation coming out of the Earth has to be 255 Kelvin. And what we find is that at 240 watts per square meter, so that's right here, if we assume no greenhouse gas, which means that the pressure at which the radiation is occurring is going to be right at the surface, we see that this is going to be right at 255 degrees. So that means that we would be re-radiating at 255 Kelvin at the surface. But if we assume that the pressure at which the OLR is located is about 0.6 of the pressure at the surface, what we find is that we are actually radiating at 288 K. So the average temperature at the surface of the Earth is 288 Kelvin, but at the altitude at which we are re-radiating back to space, that has to be 255 Kelvin. So we are going to have this drop in temperature as we go from the surface up to the radiating height, also called the effective emission height. And that should make some sense. We all know that the atmosphere cools down as you go higher up, so the effective emission height, the height at which we are radiating heat, is not going to be right at the surface, but it's going to be somewhere above the surface. But it has to be 255 Kelvin in order for the energy going out to be equal to the energy coming in. So to summarize so far, what we found is that the E in, the amount of energy coming in, on average is about 240 watts per square meter. The energy radiated back out to space from the Earth, therefore, would have to be 240 watts per square meter. Because remember, if we are in energy balance, then the E in is equal to the E out. And because we know that the E out has to be 240 watts per square meter, we know that the temperature at which we need to radiate heat away is 255 Kelvin. And so what we see is this. So this is our lapse rate for the pressure. So this is the pressure as a function of height. So climate scientists often use pressure rather than height for where things are actually taking place. And what we find is that given this pressure lapse rate, the surface temperature, as I said, would be 288 Kelvin, but the height at which we are re-radiating would be right there. So that's our P rad. And so what we find is that that is at 255 Kelvin. So 255 Kelvin is achieved at about 500 millibars right there. So this is further up in the atmosphere. What happens is if we start adding more carbon dioxide, then the height at which we re-radiate away is actually going to go up. So that means we are going to go up this pressure gradient here. So now we are going to be re-radiating right there. That's our new pressure of radiation. And what we find is that this is at 248 Kelvin, which is colder than 255 Kelvin. So now we would actually be radiating at a lower temperature, which means that we would actually not be radiating as much energy. So in order to get back into this energy equilibrium, what we would actually have to do, and I put this box here because we want to pay attention to what's going on at the surface here, we would actually have to move this over. So now we would be at 255 Kelvin again. So that would be where we are radiating. But now we see that the surface temperature is at 293 Kelvin. So because we have to radiate at 255 Kelvin, because that is the temperature that we would re-radiate in order to get rid of as much energy going out as we have coming in. And so we see that we have to reestablish radiation at 255 Kelvin in order for the amount of energy going out to be equal to the amount of energy going in. But now we've shifted this pressure lapse right here over to the right. And so that means the surface temperature must also go up. So I also used the analogy in the previous video of like heating up a pan. We know that we can't heat it up until infinite temperature, because once it's at a certain temperature, it's going to radiate the heat away at the same rate at which the stove is putting it in. So this is now our new P rad. And again, we see that the 293 Kelvin is greater than the previous 288 Kelvin. And so that's why adding that extra carbon dioxide, that extra greenhouse gas, is going to increase the surface temperature, because it has to increase the height at which we are radiating the heat away. And so this is the Boltzmann distribution for 288 Kelvin. So right here, this smooth line. But what we see is that what's actually going out, the outgoing long wave radiation, looks more like what's here in purple. And so we see this is a bit less than what we would actually see for the 288 Kelvin. And a few of the places where it goes down a lot is because of the water here. Water is a greenhouse gas, so is ozone, but so is our carbon dioxide. In fact, the carbon dioxide ends up absorbing right here in the middle of our outgoing long wave radiation. And so that's why the CO2 acts as a greenhouse gas. And this right here becomes very important. There is quite a bit of controversy about how to interpret this, because what ends up happening is with the CO2, if you add more, this dip does not actually go down further, but it does get wider, but it only does so by very small amounts. But we will talk more about that in video 4. For now, we just need to know that the CO2 is acting as a greenhouse gas, and we can see how much less the OLR is than what the OLR at the surface is. So again, the purple is the OLR at the effective emission height, and this salmon color here is the OLR at the surface. And so the area difference between this Boltzmann distribution right here and then the stuff in purple is caused by the greenhouse effect. And by the way, this is between the 10 micrometers and 20 micrometers. So this figure right here has it in frequency, but this is in that same place where the carbon dioxide absorption is centered at right about 15 micrometers. But anyway, what this looks like is this. So we have our pressure lapse rate, where we see at the surface it's about 1013.25 millibars. Then up here at the tropopause, it's about 250 millibars, where the tropopause is on average about 10 kilometers. Again, that's going to change depending on where you are on the planet, which is why climate scientists tend to like to use the pressure, because that tends to tell you more about where things are happening. But we also end up with this temperature lapse rate, where at the surface we saw that it was 288 Kelvin, then up here at the tropopause it would be 223 Kelvin, but we have the incoming solar rays, and we also have the reflected solar rays from the albedo. This would not be all from the surface. A lot of it actually comes from the clouds, but here I don't show any clouds, so I'm just showing it coming off of the surface. But we would also have the OLR at the surface. So this is the energy coming off of the surface here, which would be this Stefan Boltzmann constant right here times the temperature of the surface to the 4th power. But I have it stopping right here before it goes all the way up, because this is the so-called effective emission height. So that, like I said, has to be 255 Kelvin. So the effective emission height is at the temperature at which we need to radiate back out into space in order for the OLR to be equal to the energy coming in from the sun. So from the effective emission height, we will have the outgoing long wave radiation, which is equal to this Stefan Boltzmann constant times the temperature at the effective emission height to the 4th power, and this will be less than the energy coming off at the surface. And we know this for for one, because the temperature is higher at the surface than at the effective emission height, but also because we have this back radiation. So that's what the greenhouse effect is doing, is preventing this energy from actually going back out into the space in the form of OLR. So we have this EBR, which is back radiation. That's what's actually going to heat the Earth, where we see that the E excess is equal to the E in minus E out. So that's just our energy balance right there, where in this I've modeled the E out as the albedo plus the energy at the effective emission height. And the E in is the energy from the sun plus the energy of the back radiation. And so that's what's going to cause the greenhouse effect. But we know if we add more greenhouse gas, that what happens is this effective emission height actually increases. So it goes up to there, that's 248 Kelvin. So we are now emitting at a lower temperature, which means it's emitting less energy right there. And so that's our new effective emission height. And so what happens is the greenhouse effect just means that in order to get back into energy balance, we need everything to heat up. It has to heat up about the same amount up this entire column right here. So the lapse rate is not going to change, but everything is essentially just going to get added to it. So now we have the new effective emission height up here. So when the Earth warms, this goes to 255 Kelvin at this higher altitude here. And so everything below that has to warm up. So now the surface temperature has gone from 288 Kelvin to 293 Kelvin. And so, like I said, that's our new effective emission height. One thing that we need to keep in mind, though, this effective emission height is a way of modeling this, but we know that there is going to be absorption and emission everywhere below that. So there's going to be some absorption and emission here, and here, and here, and here, and so on, all the way down to the surface. And I have this as a gradient here because the partial pressure of carbon dioxide, for instance, is going to change at about the same rate as the total pressure here. So we see that down further, we are actually going to have more CO2 than we do up here. So there's actually going to be more absorption going on down here. This will become important when we get to video 4, and we want to talk about how carbon dioxide actually behaves as a greenhouse gas. But this is something to keep in the back of your mind, because there is a popular denial argument for climate change that essentially says that we are saturated with carbon dioxide, but that takes as an assumption that the carbon dioxide is not in a gradient, but just is at the same partial pressure all the way up to the effective emission height, at which point it just stops. But the effective emission height does not tell us where the carbon dioxide in the atmosphere actually stops. It just tells us where the carbon dioxide concentration is going to be low enough that anything that's emitted from the top here is not likely to actually get captured again by another carbon dioxide molecule. And so this also explains why the surface is warmer than somewhere further up in the atmosphere, because again, we have that incoming solar radiation. So that's our E sub sun right there. And what's going to happen is some of this is going to get reflected out, and some of it is going to re-radiate as blackbody radiation. But because we have this greenhouse gas in our atmosphere, then we can have some of that radiation get captured and focused back downward. So that would look like this. So these are the OLRs at different altitudes. And so what we see, I've modeled this as essentially a 2-layer atmosphere right here, where at H equals 1, we have one layer of our carbon dioxide. At H equals 2, we have another layer. And we're going to have more at H equals 1 than at H equals 2 because of the gradient of the partial pressure of carbon dioxide. Of course, as we saw earlier, it's not actually these 2 layers. It's actually a gradient that's continuous going up, but we can model this as 2 layers. And so at the first layer, we're going to have some of the back radiation coming back down. We're also going to have some coming back down from the second layer. So what we find is that the energy in this layer between the surface at H equals 0 and then this one at H equals 1 is the energy coming in will be from the OLR here at 0 and from the back radiation at 1, but also the back radiation at 2. Then we subtract the OLR at 1 because that's the energy escaping out the top of this section right here. But then when we get up to here, we see that the energy between H equals 1 and H equals 2 will be from the back radiation of 2 and the OLR from 1, subtract the OLR coming out of the top there. And so now we see that we actually have fewer terms right here. So we're not getting as much heat because we're not getting the heat that's actually going back down from this first layer right here at H equals 1. So that's why there is more heat in this lower layer than there is in the upper layer. And the result of that is that we'll have warmer temperatures at the surface than we will further up. But like I said, this is a gradient, and if we increase the effective emission height, now we have this gradient going further up. So instead of just this, we now have to add another layer onto it. So that's our DOLR2, and so that gives us more back radiation going on there. And so now what we see is we have this extra term right here, this back radiation 3, so we are now warming up even more in this first layer. Then when we get to this one, we now have this extra back radiation 3 right here as well, so we're getting more energy in right there, so that will also be warmer. And then up here we have the back radiation from 3, but also the OLR coming from the layer below it. Subtract the OLR from the top right here, because that is energy escaping back into space. So now what we see is that the surface temperature will go up to 293 Kelvin, but the temperature at which we radiate has to stay at 255 Kelvin. But now that this is further up, now we have a temperature lapse rate that's at the same rate, but now because this is further up, we actually get to a higher temperature as we get down to the bottom here. And so adding that extra greenhouse gas increase the altitude at which we are radiating back into space, and so that's why it's increasing the temperature down at the surface. For real greenhouse gases, the absorption coefficient varies greatly with frequency, meaning that not everything is going to radiate back at the same altitude. So such gases act on the OLR by making the atmosphere very optically thick at some frequencies, less optically thick at others, and even optically thin at other frequencies. In portions of the spectrum where the atmosphere is more optically thick, the emission to space originates in higher and generally colder parts of the atmosphere. The infrared escaping to space is a blend of radiation emitted from a range of atmospheric levels, with some admixture of radiation from the planet's surface as well. So that looks like this. So this is our effective emission height, but we're going to have OLR coming at all these different altitudes here. It's just that the effective emission height is the average height at which the OLR is escaping back to space. And so we have the average pressure of radiation here at about 500 millibars, and the average temperature at the effective emission height is about 255 Kelvin. So like I said, the effective emission height is just the average height at which all of this radiation is actually leaving the Earth, because we have this gradient of carbon dioxide where below the effective emission height it tends to be thick enough in carbon dioxide that it's going to absorb a lot more. Above that it's going to absorb a lot less, so radiation that's emitted at the effective emission height or higher is going to have a very small chance of getting reabsorbed by another molecule because there is so much less of the molecules up there. But the concept of an effective radiating level, or as I've been calling it, the effective radiating height, nonetheless has merit for real greenhouse gases. In other words, it's a decent model for thinking about it. It does not represent a distinct physical layer of the atmosphere, but rather characterizes the mean depth from which the infrared photons escape to space. As more greenhouse gases added to the atmosphere, more of the lower parts of the atmosphere become opaque to the infrared. Again, that will be important, especially when we get to video 4, but this opacity can be a bit misleading because we do have blackbody re-radiation going on even at the lower levels. And that is another thing that the climate change deniers who want to use this carbon dioxide saturation myth often forget, is that we're not just absorbing and then just holding onto the radiation, but there is also the blackbody re-radiation. So this increases the altitude of the effective radiating level, so in other words it decreases the pressure of the radiation, which is the same as increasing the altitude. So if we want to think about some real data for this, and this is using this paper that's linked to right here, so the Earth energy imbalance between 2006 and 2020 was about 0.76 watts per square meter, but the average between 1971 and 2020 was about 0.48 watts per square meter, which has accumulated in our atmosphere an extra amount of heat that we can calculate using this. So what we have is the 4 pi r squared, which is the surface area of the Earth, and so then we want to put the radius of the Earth in there, which is 6.39 times 10 to the 6 meters. But then we have this t here, which is just the time between 1971 and 2020, which here I've converted into seconds so that the units cancel out. And so that gives us 3.81 times 10 to the 23 joules that have been added to our atmosphere between 1971 and 2020. So that's E accumulated of 381 zettajoules, where a zettajoule is 10 to the 21 joules. Just for some context, the largest hydrogen bomb energy, which was the Tsar Bomba, was about 220 petajoules. So that's only about 0.0000 0.006% of the energy that's been gained in the Earth's atmosphere between 1971 and 2020. So we would require the detonation of 17,300 of that SAR bomba if we wanted to add that much energy into our atmosphere. And one last thing I wanted to talk about here is what's called a runaway greenhouse effect, which is what we can see going on Venus. So a planet which receives sufficient solar radiation can get into a runaway cycle where the planet warms in response to absorb sunlight, which causes more water vapor to enter the atmosphere. So we can get about plus 7% more water for every 1 Kelvin that it increases. So this causes more greenhouse effect because water is a greenhouse gas, which leads to further warming and an unstable feedback loop that does not end until the entire ocean is evaporated into the atmosphere. So again, this is what happened on Venus. At that point, the water vapor in the upper atmosphere gets broken down into hydrogen and oxygen under the influence of high energy solar radiation, and the hydrogen escapes to space while the oxygen reacts with rocks. Without liquid water, the urate reaction, which turns CO2 into limestone, cannot take place. So all of that outgassed CO2 just stays in the atmosphere. So the runaway greenhouse theory gives rather precise predictions about the circumstances under which a runaway can occur and explains why Earth did not undergo a runaway, unlike Venus, despite the fact that it has a water ocean. So this is that OLR spectrum here now for Earth, for Venus, and for Mars. If this looks reversed from the previous one, it's because it is. This is in the wavelength rather than wave number, so everything is just kind of reversed. That's why the O3 is over here now. But anyway, what we see is that Earth does have more OLR, where Venus has quite a bit less. And the reason for that is because Venus has a very high albedo, but also because it has a lot of greenhouse effect going on. Then Mars, which is quite a bit further away from the sun, is not going to be picking up as much energy, so it's also not going to be losing as much. But we can see all of them have this CO2 dip right here. And this is just some data right here that I've gathered. So this is for Mercury, Venus, and Earth. And the things to pay attention to on here is the fact that the E in, so the energy coming in for Venus, is actually less than the energy coming in for Earth. That's despite the fact that Venus is quite a bit closer to the sun than the Earth is. But this seems strange because the temperature on the surface of Venus is actually greater than the temperature of the surface on Earth. So how can something that's actually gaining less energy be a lot hotter than something that is gaining more energy? The reason for this is because the OLR on Venus is quite a bit less than the OLR on Earth. And we can see that one of the reasons for this is because the amount of carbon dioxide in Venus's atmosphere is a lot higher than on Earth's. So in fact, Venus is mostly carbon dioxide, about 96.5%, where Earth is only about 0.0424%. And this is also despite the fact that there is a lot less water in the atmosphere on Venus than there is on Earth. So again, one of the arguments that often comes up from deniers of climate change is that water is the main greenhouse gas, which is true, but carbon dioxide is also a greenhouse gas. And so even though there is considerably less water in the atmosphere on Venus, all of this carbon dioxide is leading to this greenhouse effect right here for Venus. Checking back in on our syllogism here, like I said at the beginning of the video, we're not really going to establish any of these, but we do further justify these three I have here highlighted in yellow. So we've further justified that if CO2 is a greenhouse gas, then increased CO2 concentration in the atmosphere will cause more energy to enter the Earth's atmosphere than leave it. P4, if more energy comes into the Earth's atmosphere than what leaves it, and there is no other mechanism for mitigating the extra energy, then excess energy will be added, leading to increased global average temperatures over some time delta t. And we saw in this video how that actually works. Then we also further justified this new one that I added here, which if a thing does something that causes radiative forcing, resulting in increased or decreased, if that's the case, global average temperatures, then that thing is at least one of the causes of climate change. Then one last thing I wanted to do in this video, because even though this video is quite long, I don't really cover everything in all of the detail that it could be, is there are some videos here that you should check out. So these three here actually do some experiments that show that the greenhouse effect actually does work and that carbon dioxide is a greenhouse gas. So these 3 videos, they all run relatively similar experiments, but at different levels of sophistication, where this one at the top is one that you could literally do at home if you really wanted to. Then these other videos, which also explain the greenhouse effect in a similar, but maybe in a way that you might find more useful. And so if you've watched this video and you're starting to get it, then I would highly recommend watching these videos as well in order to really solidify your understanding of how the greenhouse effect works. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.